When we think about not getting an infection at all, we think about preventing infection, the first person that we really have to think about is Edward Jenner. He was a doctor in the late 1700s, early 1800s, and he was familiar with this process of variolation. Remember, we talked about the blowing the smallpox particles up the nose. He also was very likely aware of an observation that people who had previously had cowpox infections were resistant to smallpox. So he had a hypothesis, and that's in science, that's like a prediction, right? He had a hypothesis that if he used cowpox material, he could protect against smallpox. And that would be even safer than using smallpox material to protect against smallpox, because most people who got cowpox didn't die. So he had to test his hypothesis, of course, and he used the 8-year-old son of his gardener in order to test his hypothesis. Now, hopefully you're going, what? Like, why would he do this in a child? Why not use an animal? Well, smallpox does not infect animals. Smallpox is only a disease of humans. Only humans get smallpox. So you couldn't do this in animals. Other pox viruses like cowpox or mpox, those can go in lots of different species, but smallpox is only in humans. So what Jenner did was he found a milkmaid who was infected with cowpox. So a milkmaid is a woman who milks cows. He took some of the cowpox material and injected it into the gardener's son, James. When he infected James with the cowpox pus from the milkmaid, James got cowpox, a very mild case of cowpox. So he did that. Then he, Edward Jenner, collected scabs from a smallpox patient. He then injected those into James. So remember, James has never had smallpox. He just had cowpox. He got over cowpox. And now he's being tested by being infected with smallpox. But James did not get sick. He was protected against smallpox. And Edward Jenner did this a few more times, like tried to infect him, and James never got smallpox. So the protection was complete. He eventually published his studies. Scientists debated over the results because that's what we do. We like to debate things. Eventually, the British government banned the process of variolation. You can no longer like blow smallpox up somebody's nose. You can't inject them with smallpox scabs. Instead, you can do the vaccination. You can use the cowpox material to protect against smallpox. So they provided vaccination free of charge. Sounds very familiar, right? Like recently, the US government provided COVID vaccination free of charge. Some people would still get smallpox, so the vaccination didn't always work perfectly. Just like with the COVID vaccine, sometimes people got vaccinated against COVID, but still got COVID. Generally though, if a patient had been vaccinated against smallpox and then they got smallpox, it was a much more mild infection compared to somebody who had never been vaccinated. Just like what we see with COVID. Sometimes people who were vaccinated against COVID got COVID, but it was almost always way less severe. People who were vaccinated almost never, but sometimes almost never, were hospitalized and almost never died of COVID. So it provided way more protection than being unvaccinated. Now, because smallpox only infected humans, if you protect all the humans, the virus goes away. And we'll talk more about disease eradication a little bit later, but this was the first disease to ever be eradicated in nature. One of our next kind of vaccine gurus was Louis Pasteur. We talked about him before in terms of identifying that there was no such thing as spontaneous generation. He noticed that when he had an old and weakened cholera culture, it protected against cholera in chickens. Chicken cholera is different from human cholera, but you'll notice this trend here where people just leave stuff out for a long time and see what happens. And so that's what he did. This was, of course, an accidental discovery. He didn't mean to leave the culture out. He and his assistant both went out of town and forgot the culture. So when they used it to try to infect the chickens got sick, but not that bad. And so then he thought, I bet if I try to infect them with a strong bacteria, fresh, not old, they'll be protected. And they were. So he was able to vaccinate the chickens. He applied that same principle to create an anthrax vaccine. He weakened the bacteria using high levels of oxygen, and that provided protection against anthrax. He also developed a rabies vaccine. He dried out infected nerve tissue from rabbits. And that weakened the virus enough that when he tested it in dogs, it provided protection against the strong rabies virus. And then he used it in a 9-year-old boy who had been attacked by a rabid dog, and it worked. The thing with rabies and the rabies vaccine is you don't have to get it before you're attacked. The virus is pretty slow at replicating. So if you've been bitten by an animal that could have been rabid, as long as you go to the hospital pretty soon, you can get the vaccine and be protected. If you wait too long, though, the virus will replicate, and rabies is almost always fatal. In fact, I don't. There's only been a handful of patients, like maybe 4 or 5, who have ever survived rabies infection in the US. So it's almost always fatal. So Jenner came up with vaccination in the first place. Pasteur created a few more vaccines. And now we have who we call the Granddaddy of Vaccination, a scientist named Maurice Hilleman. He developed upwards of 40 vaccines. He also contributed to discovering adenoviruses, which cause the cold, and hepatitis viruses, which cause liver disease. The first vaccine that he worked on was against a virus called Japanese bee encephalitis. It's transmitted by mosquitoes. And this was a really big problem during World War II because soldiers that were fighting in the Pacific theater, so in Japan and in Asia, were really suffering from this virus. He also then worked on a flu vaccine. He was one of the first scientists to realize that the flu was different every year. There were different strains or varieties of the flu that came around. In the 1960s, he was the leader of the teams that developed MMR, right? Measles, mumps, and rubella vaccines. And the mumps strain that was used to create the vaccine actually came from his own daughter. So when his daughter was sick with mumps, he isolated the virus from her, and he and his team used that to develop the mumps vaccine. In the 1970s and 1980s, he led the development of vaccines against meningococcus, which causes really significant meningitis, pneumococcus, which causes pneumonia, the swine flu, and hepatitis B. He retired in 1984, but he also worked on, prior to his retirement, the development of vaccines against hepatitis A and chickenpox. And both of those vaccines were licensed in 1995. Okay, so he's the granddaddy of vaccine development. And some people say that because of all of his work on vaccines, that he may have saved more lives than any other single person in history. And that's a pretty incredible legacy to leave behind. So the last vaccine I want to talk about really quickly is the COVID-19 vaccine, because of course that's one of the newest ones. There were a lot of individuals who worked on this and built on the ideas of each other. And so this first group here, Dr. Catalin Carrico and Drew Weissman, they're shown right here. They were the scientists who really developed the idea of using mRNA as a vaccine. They weren't specifically working on the COVID-19 vaccine. They've been working on this idea for years of using mRNA-based vaccines. But then, of course, scientists working at Moderna and at Pfizer, so Dr. Kizmika Corbett and Drs. Ugur Sahan and Özlem Turiki, working at Pfizer, were really the leaders of the development of the two major mRNA-based vaccines. So if you've been vaccinated against COVID-19, which you should have been, you most likely got a Moderna or a Pfizer version, and it's all based on the technology developed by these two scientists here. And just last week, so very early October, Drs. Katalin Kariko and Drew Weissman won the Nobel Prize in Medicine for their discovery of how you could use mRNA-based vaccines, which led to the development of the COVID-19 vaccine.